Thanks, Rob, and thanks to everybody here. It's a pleasure to address you all. I apologise that I'm doing the presentation. It was to be Joel, our European manager based in Vienna, but unfortunately he had to go to France on an urgent matter at the last minute, so that's why I'm here. The title of the presentation today really is about development of a new burner, the Turbuflex. And this is kind of a case study on leading up to the development of that burner. As Rob mentioned earlier, FCT, for those that are not familiar with the company, has three operations. One is the fact that FCT in fact produces the flames for most of the major sporting events around the world. So I'm sure everybody here has seen FCT flames, whether you knew it or not. So starting with Sydney Olympics and London Olympics and Beijing and Rio and Winter Games and Pan American Games and European Games, I'm sure you've all seen FCT flames before. The second part of our business is to do with instrumentation. We have a very unique patented technology, real-time online XRD mineralogical analysis of cement or other materials in real time. But the main part of our business, the bigger part, and the one that I'm talking about today, is our industrial combustion side. We have been involved in supplying many burner systems to many people around the world. The cement industry is one of our major customers, and the burner that I'm talking about today has got particular relevance to the cement industry. Our operations, we are Australian owned. It's an Australian company. I live in Australia, but we have operations in different parts of the world as well. And we've been growing, particularly in the last 5 years, and spreading our wings to many regions. One thing I should have mentioned before is the company has been in operation for 35 years. Certainly cement is a major industry for us, and we have many references around the world. In industrial combustion, we deliver kiln burners, calciner burners, various other kinds of burners, and including the ancillaries that go with that, valve trains or trolleys or fans or burner management systems and so on. And we also do a number of projects that don't involve equipment, consultancy-based problem solving, usually around the combustion issue. And for that, modelling is a key competency of the company. When the company began in 1984, in fact, it began with modelling as its major innovation. And at that stage, it was physical modelling. So some of you may recall some of these kinds of images where in those days the mixing of air and fuel was simulated in a liquid environment, certainly very technical to determine how to run these models. But back in those days when fuels were conventional, the combustion process was pretty much limited by the mixing. So if you mixed air and fuel together, the burning was instantaneous. That's no longer the case with alternative fuels, where in fact the combustion process is often the slowest of the processes. So FCT began CFD modelling in 1992, I think it was. Back in those days, I remember buying a computer in the US that could do modelling at a reasonable speed. It cost something like $75,000 US. Now your mobile phone probably has got similar capability. But certainly in those early days, CFD was more a curiosity. It was used on a few projects. I remember we were involved in designing the Alcoa calciner using CFD modelling. It was a project that ran for several years. CFD modelling was very labour intensive, very costly to do. But over the years things have obviously improved with faster computers, better software, and so on. And so these days, CFD modelling is the major modelling tool for FCT. And that's coupled with some other forms of modelling that I won't talk about yet today. So, getting back to burner design. A burner designer, and we are burner designers, is our fundamental core knowledge. Designing a burner, there's a number of things that a burner designer needs to take into account. And one of the first things is the temperature profile you need in a particular kiln. So in some kilns you need a short, hot profile, as in the cement industry. In others you need a long profile to give the material time at temperature. And so if you're a burner designer, you need to know what sort of heat profile you want for this particular kiln. The fuel properties are obviously very important in terms of how they will burn and how the heat's going to be released. Secondary air temperature, very, very important, and secondary air velocity, they're important considerations in burner design. The way that fuel and the air are going to mix in your particular design, the momentum of the burner, the swirl ratio, and then there's the mechanical considerations, the cooling effect and so on of the particular burner design. So these are the sort of things that a burner designer grapples with. The face plates of burners have changed over the years. There used to be open channels for air and so on. These days it's more a face plate with drilled holes. The reason for that is better stability and long-term consistent performance of a burner. But even here, and this is important in what I'm about to announce today, but the way these holes in the burner faceplate are drilled have an impact on the kind of flame that you will get. So as you, in this particular instance, as you reduce the number of holes, there is a difference in how the flame is produced and what it looks like and its properties. So if we look at the heat profile, and this is, I suppose, typical for a cement kiln, there is a peak radiation coming from the flame, and in particular the amount of heat that you're going to transfer from the flame to the product in the kiln. And this is the key thing. The more that you can transfer to the product that you're trying to heat in the kiln, the more efficient your burner is, and the lower your back-end temperatures. Conversely, the less heat that you can transfer to the product, your back-end temperatures go up and you lose efficiency. So in this particular case, this is a key thing that we look at in the burner design. So if you look at the face plates that I showed earlier, you can see that there is a significant difference in the heat profile you'll get in a kiln depending on what this faceplate looks like. I'll come to why that is shortly. But you can see that even these finer points in a burner design can be quite critical. So if we look at the properties of these two extremes, if you like, of faceplate design, in the case where we have more even holes distributed around the circumference of the burner, what that tends to do is it provides you with a less intense flame. That the fuel and air will actually mix slower that way. You tend to have lower flame temperatures, and you'll get lower NOx. On the other hand, if you have the design where the holes are separated by areas where there is no airflow, you get actually more intense mixing and high temperatures and higher NOx. And the reason for that is the primary air effectively creates turbulence between the fuel and the secondary air to promote mixing at the boundaries. So if you have the holes separated out as we have in the upper case, there is more room for the secondary air to mix, to get in between the air streams and mix with the fuel. So you get more intense mixing. And more intense mixing means that you have higher flame temperature, which is good for efficiency. On the other hand, it's not so good for NOx. So continuing on with this theme, what are the implications for burner design, because there are many instances where people have different fuels and they're not quite sure what they're going to use tomorrow, let alone next year or in 5 years' time. So what we wanted to do was to try and develop a burner that can cater for these sort of changes that often people don't know when they order a burner. So we've taken these two extremes of burner operation and merged them into a single burner. So in fact, our TurbuFlex burner is a burner that has two modes of operation. There is the standard operation, where there is the evenly spaced number of holes around the circumference of the burner. And for a conventional fuel that has good properties, this is typically what would be used. And it has another operation where there is a switching where all the air will come in 6 separate areas on the faceplate of the burner. And what that, and these are some of the CFD studies that were done to determine how best to do this. But what it means is that there is a standard mode of operation and a boost, which would be used with alternative fuels. The standard fuels, they mix adequately, they produce an adequate flame. Often NOx is an issue, so you try and minimise NOx, hence you try and slow down the mixing. On the other hand, with alternative fuel, NOx emissions are rarely an issue. The alternative fuel suppresses flame temperature and therefore reduces NOx formation. But we have the problem of a longer flame that affects the clinker quality and the efficiency of operation. So in that case, if you're using high degrees of alternative fuel, the boost mode would be the one that would be used on this burner. What does that, again, these curves represent the heat that's transferred from the flame to the product, and we can see that this is actually with coal, how that changes if you operate between standard mode or boost mode. And in boost mode you have much higher peak flame temperature, better heat transfer to the product, and so on, but then it will produce more NOx. This is a coal operation, the standard mode, what the flame will typically look like compared to the high boost mode. The flame is shorter and hotter when it's boosted. Now the same sort of information when alternative fuel is being used. We have typically when RDF is used, that will reduce the flame temperature and the radiation of heat to the product. And the more when this is used in boost mode, that recovers some of that loss of temperature and loss of radiation to the product in the kiln. Again, just some visualisation of the flames. And more curves that show what the radiation is from the flame to the kiln material with differing amounts of RDF. So that is really getting towards the end of what I'm presenting today, which is the development of the TurbuFlex, the reasons for it, what the science behind the development of this burner type. The first of these, prototype proof of concept, has been in operation in Europe now for over a year. And everything we've expected from that has proven to be correct. We are currently in the next week or two delivering another 4 of this burner design in Europe, which are in a way the first of the commercial burners that are being delivered in Europe. So hopefully next year I'll be able to tell you more about the results of that. And this is, I guess, the final diagram, which shows the various channels in the burner and the air distribution system, primary air distribution for that burner. This was the trial burner. Okay, I think, and these are the latest ones under production. Thank you very much. That's all I have.
So thank you very much indeed, Con, for giving us a quick overview of how burners work. Always good for a refresher. Are there any questions from the floor? If you have questions, please. Yes. Leos Waleski.
Thank you very much for an interesting presentation about this burner, and I would like to ask you about the dimension of the RDF channel in this burner, of the diameter, as you've shown us in one of the previous slides. There were the channels, and what is the diameter for the RDF?
Well, typically an RDF pipe will be between 100 and 150 millimetres. There's no one size. It depends on a number of things, including the amount of fuel that is meant to be transported down the pipe and the sizing of the alternative fuel. We have at times produced a size that is 80 millimetres when the proportion of alternative fuel is less, but the size of the material will limit going any further down with that. The injection velocity of the alternative fuel can be important. It can be between 25 and 50 metres per second, usually around the 30 metre per second mark, but it depends on what the material is as well. And so the bigger the pipe, the more conveying air that is needed, and that provides some inefficiency in the burner itself. So the idea is to use the smaller diameter that we can, depending on the size of alternative fuel.
Understood, thank you. I know that there is some proportion. If we want to increase the feed rate in the main burner, it is always good to have a little bit bigger diameter of this channel. So it is for you the limitation. And I understand that if you have a bigger diameter of this RDF channel, then you will add there more air, which you would like to avoid. So is there for you any limitation? Limitation is 120 millimeters, or you can go a little bit higher?
Well, all those things are considered when the burner designer designs the burner. And the things you mentioned are the important things. How much air is going to be needed down this alternative fuel channel, because that is a loss of efficiency, the more air that you need. And the bigger the diameter of that pipe, the more air you'll need to keep the velocity where it needs to be. So that is a key consideration. On the other hand, if the burner pipe is too small, you could get blockages. So it needs to be big enough to avoid those blockages. And if you're looking to use very high percentages of alternative fuel, then that also will increase that pipe diameter a little bit also. But these are all the levers that a burner designer has to play with to try and come up with the right design of burner.
Thank you very much.
Thank you. Thank you, Leos. Okay, so we have another couple of quick questions here. Is there a measurable effect of having larger and smaller holes in normal mode rather than just smaller ones?
Now, I'm not sure if I get that question completely. So we're talking about having more holes and smaller holes. I mean, we've looked at an example of 36 holes. Of course, in the extreme, that channel becomes an open channel. So there's no longer holes, it is open all the way around. It is one extreme. Look, in principle, the more holes you have, the closer it comes to having an open channel. And that, in fact, does slow down the mixing of secondary air with the fuel. The less number of holes, and all these burners, by the way, were designed with the same total momentum. So whether you're putting that total momentum distributed through 36 holes or 72 holes compared to a limited number of holes, then the mixing becomes more effective if you have a smaller number of holes and directing all that momentum through a smaller number of larger holes.
Okay, if you didn't quite get the answer that you wanted, Con has a exhibition booth directly outside the doors here on the right hand side, so you can ask him more about that. Another quick question: does having a more complicated burner than other products have any drawbacks, like a higher failure rate due to complexity?
Look, that is a really good question. One of the things that we do strive is to provide the simplest possible burner. You will all know there's some quite complicated burners on the market with movable parts. You'll see FCT burners do not have any movable parts. In terms of the switching arrangement for this particular burner, there is a valve at the back of the burner. Our face plates don't have any moving parts. Anything that is moving in the hot part of the burner is subject to failure, and so there's no moving parts in the burner at all. Any control is done at the cold end outside of the kiln.
Very sensible. So final question. You mentioned that you get a 25% or up to 25% reduction in NOx when you're using this burner. Is that just with regard to alternative fuels, or could it actually apply to conventional fuels as well? And is it in comparison with which other burner is it in comparison?
There's a 25% roughly difference in NOx emissions between our boost mode and the conventional burner mode. So the boost mode provides a much more intense flame, but it produces high NOx. Now, the high NOx is not such an issue with alternative fuels, but you need a more intense mixing with alternative fuels to provide a flame heat profile that's getting similar to what the coal was. So it is in comparison with our burner, but it's generally true. Our burner is similar to many other designs in some ways. So the relative difference, whether you're using the high intensity mixing or the less intense mixing, there's about a 25% difference in NOx. For coal, that could be an issue. For alternative fuels, it usually is not.
Okay. Any other questions from the real world in the room? Okay, in which case let's once again thank Con Manias. Thank you.
Thank you.